What's up, folks? This is Rev Bari, Brown University physics grad student. Today, I welcome you to the next episode of Statistical Mechanics. Now, I want to start the episode with a secret. Now, this is a secret that not many physics textbooks or even physics professors dare to mention, because if they do mention it, then they'll have to explain it, which they will, of course, inevitably fail to do. This was a secret that was discovered only in the late 1970s by Ken Wilson, who won the Nobel Prize in Physics for discovering renormalization theory. What is this deep, mysterious secret? It turns out there is a deep relationship between quantum mechanics and thermodynamics, the physics of the very small and the physics of how heat moves between different objects. What is another way to phrase this connection? Well, it turns out that the physics of how magnets work in thermodynamics is exactly equivalent to the physics of why light takes the path of least time between two different points in quantum mechanics. Phrased more technically, the Ising model of magnetism in thermodynamics is exactly equivalent to the principle of least action, or the Feynman Path Integral in quantum mechanics. Now, in this lecture, and actually not in just this lecture, this is the first in a series of trilogy lectures where we're going to explore Feynman's path integral approach to quantum mechanics and how that relates directly to thermodynamics. So today we're going to start off with something pretty simple that you probably encountered all the way back in high school, which is the double slit experiment. Let's draw that back here. The double slit experiment considers a wall with two slits and a beam of light that's incoming towards these two slits. And back here, there's a wall that records any patterns, any distributions of the wave. So what happens when the beam of light passes through the slits? Well, the beam of light is going to diffract. It's going to form these spherical wavefronts. And when it does so, in some places, the two wavefronts will interfere constructively. In other places, they will interfere destructively. And so at the end, you will get an interference pattern here at the back where you have destructive interference, these troughs, and constructive interference shown by these valleys. So that is what happens when you throw light into the double slit experiment. What happens if you throw just regular billiard balls, classical particles? If you throw classical particles into the double slit experiment, well, you get what you'd pretty much expect, right? So if I throw a bunch of bowling balls into the double slit experiment, well, I'll get a bump over here where there's the left slit and a bump over here where there's a right slit. And the total, not interference pattern, but the total pattern at the end will be a combination of these two bumps, as shown over here. But now, what if I throw electrons, not light, not billiard balls? What if I throw electrons into the double slit experiment? What is going to happen now? Well, if I throw electrons into the double slit experiment, then you might at first expect them to behave similarly to the billiard balls because these are just subatomic particles, right? They're not electromagnetic waves, they're not radiation. They should probably behave just like the particles. Well, no. It turns out that when the electrons pass through the slits, they also generate an interference pattern just like light. And so what does that mean? That means that even though electrons look like particles, they're producing a pattern associated with waves. That means somehow these electrons are interfering with each other, even though they're passing through the slits looking like particles. So the moral of the story is that let's say we don't shoot all these electrons at once. What if I shoot just one electron? Okay, maybe then they're not going to interfere with each other anymore. Okay, now no more cheating, no more games. Okay, I just throw one electron at a time into the double slit. Okay, what's going to happen? Well, okay, this one electron is going to land somewhere. Okay, sure. Let's say it lands over there. I make a measurement and I find that's where the electron is likely to be. Now let's throw in the next electron. I throw them in one at a time so that they cannot interfere. Okay, I find that that electron shows up somewhere here. I throw in another electron. I throw them in separately so they cannot interfere. Okay, I find another spot where that electron lands. and so on and so forth. And what I find in the end, after I accumulate all the results, is yet another interference pattern. Even though I threw the electrons in one at a time so that they could not interfere with each other, somehow they still produced an interference pattern. Something very weird is going on. And so what we have to do is go back to the drawing board. Go back to the drawing board and think what happens when you shoot in just a single electron. Is it passing through just one of the slits? No, because clearly if that were the case, then we should not get an interference pattern when you throw in electrons one at a time. That means even when you throw in one electron at a time, somehow it looks like it's going through both slits. In other words, the electron is interfering with itself. And so what we have to consider is the electron not passing through one slit, but both slits simultaneously, as if the electron split up, went through the two slits, and then bloop, went back to its original self and hit the wall somewhere. So the moral of the story, the takeaway, is that we have to consider the electron going through both slits at the same time, not just one. Even though it's just one electron, the interference pattern that results seems like it's somehow interfering with itself, which suggests that the electron is somehow going through both slits at the same time. And now we're starting to approach the idea of Feynman's path integral. So stay with me here. Let me erase all of this over here. And let's dive into this even deeper. So here's the picture that we have right now. We have our back wall right here. We have our double slit. Let me make it over here. And let's put in our two slits. And of course, we have electrons that are being shot out from over here, maybe from an electron gun. Okay? And what we just discovered is that we have to consider, even if you throw in just one electron at a time, you have to consider the electron traveling through not one, but both of the slits simultaneously in order to reproduce the experimental interference pattern that you see on the back edge of the board. So, okay, what's the big deal here? This is the double slit experiment, right? Why doesn't anyone talk about the triple slit experiment? What if I added in a third slit over here? What, are physics teachers too scared to talk about it because they can't answer the physics questions associated with this? Well, Mother Nature answers this question every day when you look at a light bulb. What happens is that if you add in a third slit, now you have to account for the electron going through the third slit as well. Okay, well, why stop there? Let's add in a fourth slit, and a fifth slit, and a sixth slit. Now you have to consider the electron going through all of these slits simultaneously. Okay? Well, why stop there? Now we have one edge right here. We have one 6-slit wall. Why not add another wall? Okay? And in this next wall, I'll also add some slits. Here are more slits. But now things get complicated because you see, now we've just not only doubled, maybe tripled the number of possibilities for the number of paths that the electron could take. Why? Well, consider this. Let me use a different color. The electron could, for example, go to the first slit of the first wall, but then it could go to the first slit of the second wall, or the second slit of the second wall, or the third slit of the second wall, or the fourth slit of the second wall, and so on and so forth. And so let's erase all of this and let's start from scratch. What's the big picture here? The big picture is this. If you have not a double slit, not a triple slit, not a quadruple slit, but an n-slit wall, and not just one of these walls, but n of them, okay? And here is finally the viewing screen. Let's say you have an electron right here. What you have to now consider are all the possible paths that this electron could take from point A to point B. Okay, and what are all those possible paths? Well, let me just illustrate one of them. For example, the electron could choose to go through this last slit of the first wall, but then it could choose to go through the second slit of the second wall, through the fifth slit of the third wall, and so on and so forth. You have no control over the electron. Instead, you have to consider all the different possible paths that the electron could take to get from point A to point B. So these are just a sample, just a small sample of all the possible paths that the electron could take from this starting point to this ending point. So what Richard Feynman had an idea. He thought, okay, the electron does not discriminate between any of these paths. No, it takes all of these paths simultaneously. And so each of these paths must be taken into account when the electron hits its final position. So how do we take into account each of these different paths? Well, what Feynman suggested is let's attribute something called an action to each of these paths. So for example, let's call this first path, path number 1, okay? We'll say that this path 1 has an action S1, where S stands for action, just by convention. What is action? Action is just a number associated with a path. So for example, maybe this path has an action of 5. What are the units of action? Well, we'll get into that later. But suffice it to say, the action is the integral of the Lagrangian times time. And the Lagrangian has units of energy, and time, of course, has units of seconds or time. So the action has units of energy times time. Okay, so it could be something like joules times seconds. But that's besides the point here. The point is that each one of these individual paths from the start point to the end point has a different action associated with it. So S1, for example, might have an action of 5. This second path might have an action of 10. The third path might have an action of 14, whatnot, right? What Feynman told us is that in classical mechanics, it is only the path of least action that matters. See, if this was a classical particle, then the electron would only take the path of least action, which in this case is S1, which has an action of 5. But this is not a classical particle. This is an electron, right? And so it's not just the path of least action that matters. No. It's all the paths with all their different actions that matter. So what Feynman proposed is that the true path of the electron is going to be determined by democracy. It's going to be determined by summing over all the possible paths. Okay, this is a sum over all the possible paths where each path has an action S associated with it. And because we need to make sure this action has the right units for quantum mechanics, we introduce an h bar, okay? Divide the action by h bar and multiply it by I and exponentiate this. This right here, ladies and gentlemen, is the basic idea behind the Feynman Path Integral. Okay, it says that each path that the electron could take has an action S associated with it. And so you sum over all the possible paths. And once you sum over all the possible paths, then you get an answer. You get a result. And that result is the final position, the final location of where the electron lands. So that is the big idea behind Feynman's path integral. Now that you have an intuitive grasp, let's go ahead and start taking the mathematics apart. Start with a picture. Let's say you have an electron somewhere on this blackboard. Let's say I have an electron right here. Okay, so this is the wave function of the electron, and it is peaked at this initial location. I'll call this initial location xi, and this initial time ti. Now let's say that after some amount of time, the electron has gone from this initial position to some final position. Let's say it's somewhere here. So the wave function of the electron, represented by this little peak, is peaked over here. And this is the final position of the electron at some final time. Now, there are several questions we can ask. First of all, what are the initial conditions for our electron? Well, the initial conditions are these positions and times, right? xi and ti. How can we express that? Well, we can simply write the wave function psi at time t equals 0 is given by the initial position vector r sub I, okay? So that is the initial condition for our electron. What about the final position? Well, the final position is that at some final time t sub f, so psi of t sub f is equal to the final position of the electron right there. Now we can start to ask some more interesting questions. First of all, how do you figure out how the electron went from point A to point B? Because see, it's not classical mechanics anymore. You can't say the electron took some certain path, right? Because in quantum mechanics, the electron cannot have a well-defined position and momenta at each step of its trajectory. So there's no such thing as the electron takes a particular path. But by virtue of Feynman's path integral, we can say, okay, maybe the electron didn't take this path, maybe it didn't take this particular path or this particular path, but maybe it took some combination, some weighted average of all possible paths between my initial and final points. And so here I've drawn a selection of all the possible paths between our initial and final points. Now, here's the caveat. How does my electron's wave function evolve over time? Well, I can simply use the Schrodinger equation, the time-dependent Schrodinger equation, which says that I psi dot is equal to h bar psi. Very simple, right? Or if I have to write it out, let's write it out. I h bar partial psi partial t is minus h bar squared over 2m partial squared partial x squared plus v psi, right? That's all that Schrodinger's equation says. We can use Schrodinger's equation to evolve our wave function, our initial wave function, forward in time. But there's another way as well. And what is that other way? It's to use the time evolution operator. The time evolution operator is this operator u that says that after a certain time delta t, your wave function will have evolved by a certain phase shift given by this thing right here. Now, of course, the operator doesn't make any sense in isolation, but once you apply this time evolution operator to our initial wave function, psi of 0, then you get our wave function at some later point in time, psi of t, right? So by acting the time evolution operator on our initial wave function, we get the wave function at some later point in time, psi of t. Now, here's an even more thought-provoking question. We know that when we initially have our electron here, then by the laws of quantum mechanics, by the Schrodinger equation, the electron is going to spread out. It's going to propagate in all directions. And only part of the electron's wave function is going to arrive at this xftf. So the question is, how much of the electron's wave function gets to this point? To answer that question, we need to use the overlap integral. The overlap integral simply says the amount of the electron that arrives over here is simply given by the overlap of r sub f with the electron's wave function at some later point psi of t. Okay, now we know what psi of t is, do we not? Psi of t is simply the time evolution operator acting on the initial wave function. So we can simply replace this psi of t with the time evolution operator acting on our initial wave function psi of 0. Okay, well, first of all, what is our time evolution operator if not this phase shift right here? So let me put that in right here. So we have a phase shift for our time evolution operator. That's going to look like RF, that's our final position. And our time evolution operator is e to the minus I h t over h bar. And psi of 0, our initial wave function, was simply the initial position vector, r sub I. So this is r sub I. And so this right here is how much of the electron is going to propagate from our initial position to the final position. Okay, this is how much of the electron not all of the electron is going to arrive at this final position, right? Because the electron is going to propagate in all sorts of directions according to the Schrodinger equation, but some of it will indeed cross this point, x sub f. So the moral of the story is that this is how much of the electron will come over to r sub f if the electron started from a position r sub I. And this is important enough, this inner product is important enough to get its own name. This right here is the propagator. We call it K. The propagator starts from some initial position, x sub I, initial time, t sub I, and goes forward to some initial position, some final position, x sub f, at some final time, t sub f. So that right there, let me move the camera slightly. That right there is the propagator. It tells us how much of the electron survives from the initial position to reach this final position. Now what we're going to do, the next job for the Feynman path integral, is to discretize the time interval for the propagator. What do I mean by discretize? Well, take a look at what we have here. We have the initial time t sub I, the final time t sub f. Our next job, our next business is going to be to take this time interval, t sub I to t sub f, and chop it up into infinitesimal pieces. Okay, we're going to chop up this time interval into infinitesimally small pieces, each with an interval length epsilon. And this is going to help us break down this inner product into n inner products. Okay, n inner products, where n is the number of time slices we have. And that's what we're going to do in the next part. Now let's check out how to discretize the time interval. Let's say we have some wave function. The initial wave function, let's say, is psi of 0. This is our initial wave function for an electron. And let's say we propagate this forward in time using the time evolution operator to get the wave function for the electron at some later point in time, psi of t. Now, here's the thing. Let's draw the time interval over which we propagated the electron's wave function. Let's say that this is our initial wave function, psi of 0. Let's say that this is the wave function at some later time, psi of t. And this is the wave function at the final time, psi of t sub f. Each time, I can use the time evolution operator to propagate the wave function forward. But what is this really doing physically speaking? Well, there's no easy way to picture the wave function because it's in an infinite dimensional Hilbert space, but we can try to do a decent job by plotting the wave function psi against space and time. So let's imagine that the initial wave function is, for example, this, represented by a vector in Hilbert space. So this, for example, could be psi of 0. Now, what really happens when I propagate this wave function forward in time? What does this really do to the wave function's vector? Well, first of all, I know that the wave function's length, its inner product, always has to be normalized, right? Because the wave function has to have a total probability of 1 over all space. So I know that the length of this vector won't change. So really, the only thing that this unitary operator can do is rotate my wave function's vector in Hilbert space. So that's going to look something like this. So I rotate my wave function's vector in Hilbert space by some amount theta to obtain my new wave function. The unitary operator acting on psi of 0 gives me psi of t. And voila, that's what my time evolution operator is really doing. It's just rotating my wave function's vector in Hilbert space. That's all that's happening. It's not shrinking or contracting or dilating the length of the wave function's vector because it can't. The wave function has to be normalized. So now that we know that, let's think about how we can approach the propagator. So remember that the propagator looks something like this. The propagator says that I start with some initial state x sub I, okay, and then I apply the unitary time evolution operator to end up with some final state x sub f. This should actually be flipped around. This should be x sub f here, x sub I here. And this is the propagator for xi comma ti semicolon xf comma tf. Now, we can break this up into two different pieces because first of all, I can break up this unitary time evolution operator acting on x sub I as two unitary operators acting on psi sub 0 and psi sub t. So what does that look like? That looks something like this. Let's say that instead of psi sub t, I'm going to call this t over 2 and call this t. Okay, so this is halfway to our final time, and this is another halfway to get to our final time. And this is time t equals 0. So now what I can write is that psi of t is simply equal to the time evolution operator acting for a time t on my initial wave function. Okay, well, we've written this like 5 times, so what's the difference? Well, the difference is now instead of applying psi of t, u of t to psi of 0, I can just apply u of t over 2 to psi of t. Okay, let's say psi of t was this wave function right here. So now if I apply u of t over 2, I go from the midway point to my final wave function. But I can do even better than that, right? I can apply u of t over 2 twice to my original wave function to get to my final wave function, right? So I can apply u of t over 2 once to get to the midway point and once more to get to the final point. And so now how do I evaluate this integral in integral form? Well, remember that this product is simply the identity matrix, right? If I simply integrate the outer product of the position bra and ket dx, then I simply get the identity. So now I can simply apply that over here. So I'm going to shove the identity onto here, and let's see what that does to the propagator. So the propagator is simply this, and so now I'm going to write x sub f on one side. That's one part of my propagator. So I have x sub f on one side, and then I'm going to have this part, this x over here, and in the middle I'll have my time evolution operator. Okay, and then I'll have the same thing, but now x, which is coming in from this bra, and then my time evolution operator once more, and then I have my my initial position, xi dx. Okay, and so this is how we can express our time evolution operator in an integral form. And one more thing, I should say not just the time evolution operator here, no, because I applied it twice, I should use u of t over 2 and u of t over 2. So the time evolution operator applied for half the time interval and the time evolution operator applied for another half of the time interval. Brings me from my initial state x sub I to my final state x sub f. And that's all there is to the first part of discretizing the time interval. In the next episode, we're going to check out how to go further with the Feynman Path Integral.